I'd like to welcome you to the first Carl Sagan lecture. This is an inaugural event for the new Biogeosciences section of the American Geophysical Union. This Carl Sagan lecture is also co-sponsored by the Planetary Sciences section and the Committee on Public Affairs of the American Geophysical Union and by the Planetary Society. We are especially glad to welcome members of the Planetary Society and the public to this lecture. One of the goals of the new Biogeosciences section of AGU is to enhance AGU's ability to communicate the many fascinating aspects and constraints on the habitability of the Earth and the planets, and we think by having this new section we'll be able to do that better and carry on the tremendous legacy of Carl Sagan. With this, I'd like to turn the microphone over to Jim Head, who is the president of the Planetary Sciences section and will introduce our speaker.
Thank you very much, and it's a great pleasure to be here. As you all know, Carl Sagan was very widely known for his towering intellect, his imagination, indeed the scientific breadth of his interests, and his ability to communicate even the most arcane scientific facts to the public. This is something we very sorely miss and all need to work towards. He was also known for his inspirational influence on a generation of young scientists, including myself and a number of the people in this audience here. We miss Carl's intellectual daring and scientific leadership, and we profoundly feel the communications abyss with the public left by his passing. I think this particular Carl Sagan lecture is a step in the right direction in this context, in cooperation with the Planetary Society and all the members of the Society and the Union as well. But Carl would have been very pleased with the events of today, not because the lecture is bearing his name, not at all because of that, but because of what it represents. The emergence of a Biogeosciences section in AGU is a very, very important event. And its firm connection with planetary sciences is also important, and the fruits that that interaction will bear in the future are indeed very significant. It is equally fitting that the topic of today's lecture is Mars, as you all are aware. I sat next to Carl when the first color image from the Viking lander came in. For some reason, the two of us were alone in a room when this image came in. And as a young pup of a planetary geologist, I was, of course, thinking about what are the rocks going to look like. Carl, of course, was thinking of something much more profound. And as we both eagerly watched the image scroll down the screen, very excitedly saw it one line at a time, Carl turned to me and said, "Jim, that confirms one of the findings of Paleolithic man. Mars is red." Well, it could be no more fitting, too, that the first lecture be delivered by Maria Zuber, the past president of the Planetary Science section of the American Geophysical Union, and a person who has helped lead and interpret the Mars Global Surveyor data, particularly the laser altimeter data, and the investigations that have changed our entire view of Mars way beyond anything that could have ever been imagined 20 years ago, certainly by Paleolithic man, but probably not by Carl. Maria, in fact, is the immediate past president of the Planetary Sciences section of the AGU and has been a member since 1981. She is currently the E.A. Griswold Professor of Geophysics and Planetary Science at Massachusetts Institute of Technology and a senior research scientist in the Laboratory for Terrestrial Physics at NASA's Goddard Space Flight Center. Her major areas of interest are theoretical modeling of geophysical processes, analysis of altimetry, gravity, and tectonics to determine the structure and evolution of the Earth and solid planets. Dr. Zuber received a BA in astrophysics from the University of Pennsylvania in 1980 and holds a SCM and a PhD in geophysics from Brown University. It is a great pleasure to introduce the first Sagan lecturer, Maria Zuber.
Great, welcome. Well, it's wonderful to see so many people here, especially so many people from the general public. Okay, in this lecture, it's really an honor that this lecture be named after Carl Sagan, because Carl was among the first to recognize how much could be gained by merging biology and geophysics. Okay. And so it's very fitting that we honor him in this way through this lecture series. Today what I'm going to talk about is a topic that is near and dear to Carl's heart, and that is Mars. Okay? And there are two things about Mars that I think are very relevant to the combined study of biology and geophysics. The first is trying to answer the question whether or not life might have ever developed on Mars. And the second thing is, how will we sustain life on Mars when the inevitable day comes that we send people there to explore the planet? Because whether or not there ever was life on Mars, certainly in the future there will be. And so, in order to do that, we need to answer some questions, and the questions that we attempt to answer deal with trying to understand the present environment of the planet and the past environment. Without understanding the present, we have no hope of ever going to be able to go back and try to understand what early Mars was like. And what I'm going to try to talk about today mainly focuses on what we've learned from the recent missions to Mars, and maybe a little bit about what we hope to learn from the future. Jim, is there a pointer someplace? Okay, well, what you see on the first couple of slides up here is what started all the excitement, I think. This is a Martian meteorite, ALH 84001, and the possibility was raised that this meteorite could possibly contain early biological signatures. And this is, in fact, a matter that's still being debated. But what we want to do is we want to look at Mars in a global context to try to get some idea about whether or not the conditions were really amenable for life to develop. What you see over here on the left-hand side is you see Earth and Mars to scale, and actually they have a lot of similarities. Mars is about as big as the Earth's core. It has about the same surface area as the continents of the Earth, so it has about the same surface land area as the Earth does. It has a lot of the things that we have on Earth, okay? It's got a core, it's got a mantle, it's got a crust, it's got an atmosphere, it's got polar caps, it might have once had an ocean, and so in a lot of ways, it has a lot in common with the Earth. But if we look at Mars today, it is a frozen desert. Although it has a lot in common with the Earth, and is in fact the planet that is most like the Earth in terms of its environmental conditions, it's still not a very hospitable place by our standards. Okay, these are some Pathfinder images, and you can see here the Sojourner rover, and over there the Twin Peaks. Mars today is a frozen desert. It's very dusty. The average temperature is about minus 80 degrees. Its surface pressure is less than 1/100th of the pressure at the surface of the Earth, and that means the atmosphere doesn't hold heat very well. In fact, if you could stand on Mars without wearing a spacesuit, which you couldn't, your head would be 40 degrees colder than your feet, because the sun heats the ground, but the atmosphere can't hold heat very well, so it cools off very quickly. Today, liquid water is not stable at the surface because of the low temperature and the low pressure on the surface, but it didn't always used to be that way. Earlier in Martian history, there is abundant evidence on the surface, which we have had since the 1970s, that water once flowed freely on the surface, and so we know that the early environment of Mars was more warm and hospitable. And in fact, the concept of Mars being early warm, early wet is one that's very popular. But the real question that we have here is we see places that are absolutely evidence for water flow. Here's something that's about 60 kilometers across. We see evidence for catastrophic flooding, and it's not like on the Earth where it comes down the mountains. It just starts out of nowhere. So this is probably volcanic intrusion here that heated ground ice that caused a catastrophic discharge of water. And so one of the questions that we want to ask is, how persistent was liquid water on the surface of Mars? Was there a long clement period when it was nice and warm and water just flowed? Or was it a relatively brief period of time where we had liquid water on the surface and then it quickly froze over? And so these are questions that we attempt to answer by studying the surface. Now these are some views of the surface of Mars here, and this is not the real color of Mars. Mars is actually very dusty, okay? And if you just take pictures of Mars, you don't see a lot of detail because the dust obscures detail on the surface. So what is plotted here is altitude, where reds are high and blues are low, okay? And in order to try to understand the early environment of Mars, what we would like to get a handle on is to try to explain some of the fundamental aspects of the surface of the planet. Okay, we see here that the northern hemisphere of Mars is blue, which means that it's low in elevation, and the southern hemisphere, being red, is very high. And this difference in elevation is called the Hemispheric Dichotomy, and this is one of the fundamental things about Mars that we want to understand. Okay, another thing that we want to understand is this area right here. This is an area called Tharsis, and it's an area that has large volcanoes. This is Olympus Mons, the biggest volcano in the solar system. It also contains the Valles Marineris, which is a canyon that's 250 kilometers wide and runs about the length of the United States. Okay? So there were clearly forces early in Martian history that were quite tremendous. Another thing that we have on Mars that was quite abundant here are large impacts. Here is the Hellas Basin, which is the largest known impact crater in the solar system. It's 2,200 kilometers across, again, almost as big as the United States. It's 11 kilometers deep. If you took all the material out of it and spread it over the United States, you would have a layer 2 kilometers thick of the material that fills that hole. Here's some other big impact craters. This is the Argyre Basin, this is the Isidis Basin, and buried under the northern plains here is an impact as big as this one, but it's only 2 kilometers deep, not 11, because it has been filled in with magma and sediments. So, the question that you can ask here, well, what do volcanoes and big holes in the ground have to do with whether or not life ever developed on Mars? And the answer is potentially everything, okay? Let's talk about impacts first, and we'll get back to the volcanoes later. An impact of this size could sterilize the surface. Any life that would have been developing could have been wiped out by an impact like this. An impact like this brings a lot of energy onto the surface of Mars, and it heats the interior and causes volcanism. And it would be quite a bad day if you were right in the vicinity of this, but if you were farther away from it, it could provide the conditions that might be more amenable to life developing. Another important thing about impacts is that it is the most effective way that we know of stripping the atmosphere off of a planet. You can get rid of a significant fraction of the Martian impact, of the Martian atmosphere by forming this impact crater. And in fact, this is quite important because we know, because Mars had liquid water, that it once had a much thicker atmosphere than it has now. And finally, a large impact is a source, potentially a source of water. On Earth, everywhere we have water, we have life. And so the history of water is something that we are immensely interested in on Mars. And so early on in the solar system, we had a lot of comets floating around, and every once in a while one gets close to Jupiter, and Jupiter is such a big gravitational mass that it perturbs it into the inner solar system, and some of them hit Mars. Okay. So some of Mars's early water would have been delivered by impacts. Now, one of the things that we thought before we had the recent data is that maybe this whole northern hemisphere, the blue part, was formed by an impact hitting the northern hemisphere. In fact, there's a variety of evidence that now indicates that that's probably not the case, although there are impacts buried beneath the magma that flowed here in the northern hemisphere. But here's another perspective here of the Hellas impact basin, and you can see all this high topography surrounding the Hellas Basin. And what this shows is that part of the reason that the southern part of Mars is higher than the northern part of Mars is because of the stuff thrown out of this basin here. So one of the things that an impact did is it contributed to making the southern hemisphere high. And we'll get back to this because this has to do with pathways for liquid water. Okay, now we're going to take one look here into the interior of Mars, and there we have some clues that very early on in Martian history, Mars was a very energetic place. Okay, on the left-hand side, you see magnetic anomalies that were measured by the Mars Global Surveyor spacecraft. Now, on Earth, rocks that have iron on them, when they are extruded as volcanic flows and they cool through a certain temperature, if the planet has a magnetic field, it freezes in that magnetic signature. Okay, and so if we know when a rock crystallized, essentially, we can say something about what the magnetic field was. Well, these anomalies here are 20 times larger than the largest anomalies on the Earth in terms of their magnitude. And magnetic anomalies are produced by a magnetic field which forms due to convection in a liquid iron outer core. And so we know from the presence of these anomalies that early in Martian history, it had a liquid iron core that was convecting and losing its heat very vigorously. So early Mars was a very hot place in the interior, and it was trying to get its heat out. Okay? Now, over on the right-hand side here, this is a model if you sliced Mars. Now, this is a computer model, so we can do things like this. But here's the core, and here's the mantle. And it turns out the most effective way to cool off a planet quickly, if you have a very hot core, is to lose the heat out of one hemisphere instead of losing it out everywhere. It just turns out to be very efficient to lose the heat out of one hemisphere. So this is a way of heating up one hemisphere, causing magmatic flooding, and this is a way of making the northern hemisphere covered with volcanic flows that I showed you. Okay, so here's another view of Mars then, and what the right-hand side shows is a slice going from the south pole of Mars up to the north pole. So here's the south polar cap, here's the north polar cap, and this is right along the zero longitude line, okay? And what this shows you is that if you start at the south pole of Mars and you start walking north, it's downhill all the way, okay? The South Pole is 6 kilometers higher than the North Pole, and this occurred because of the combination of this big impact throwing out material and piling it up here, as well as this vigorous loss of heat from the interior in the northern hemisphere. Okay, so the deep interior of the planet and this impact have caused Mars to have what we call a pole-to-pole slope. Okay, now the reason that this is important is because this pole-to-pole slope has controlled the flow of water in the planet's history. Okay, I want to now talk about evidence for water early in Martian history. And we're going to look at an area right in here. We're going to focus on this blue part. This is an area called Amazonas Planitia. Here's the Tharsis volcanic province, and here is the Amazonas region. And what you see here is a path of topography that cuts across this area here. And what we do here is we're comparing the height of this topography and how much it changes to other flat surfaces that we have measured in the solar system. So this is the Sahara Desert right here. It was measured. Right here is the Atlantic Ocean seafloor off the eastern coast of Argentina. Here is the flattest area of the dark part of the moon, the Mare Basins on the moon, taken by the Clementine spacecraft, and this is the smoothest area on Venus that we know of that was measured by the Magellan spacecraft. And what you can see here is that, there are parts of Mars that are extremely smooth within this blue area. In fact, you could go for hundreds and hundreds of kilometers over the surface of Mars, and the change in topography would be less than my height. Okay? It's flatter than the Midwest. It is flatter than the Tibetan Plateau. The only thing that it is comparable to are things like the Bonneville Salt Flats or the abyssal plains and the ocean floor. Okay? And this has led people to conclude that there may have once been an ocean on Mars. Okay? Now, what do we know about this? What we actually know is that Mars is flat. Okay? What we believe is that there is a heavily sedimented surface, because the only way to make a surface that smooth is to drop sediments on it. We don't have proof that these sediments fell through water and came from an ocean, although it's a good circumstantial case. What we don't find on Mars is the chemical evidence to support a global ocean in the northern hemisphere. If you have a carbon dioxide atmosphere like Mars has, and you mix it with water, you ought to get calcium carbonate or limestone. Okay? We have looked for that, and there is an instrument in orbit around Mars that, if it were present at the 10% level, it would find it. So the smoking gun for the global ocean on Mars is elusive, but the search goes on. It's possible that this is covered up by dust or only outcropping in smaller areas than we can resolve with the current instrumentation. Okay, well, just to show you how difficult the problem is to try to figure out if there was an ocean on Mars, here's the Olympus Mons volcano, and we're looking in the same area that I just showed you that profile from in the last slide set. And we're looking in this area right here, and it had been proposed before the recent spacecraft that there were oceans on Mars, and in fact that there were Paleo Shorelines. And so what you see here are some pictures that the camera in orbit around Mars right now took. And here is a blow-up of where this shoreline should be, and you look at this picture and you say, does this look like a 4 billion-year-old shoreline? And the answer is, I don't know. No one knows what a 4 billion-year-old shoreline should look like that has been blown around by dust and modified by goodness knows what. So it's very difficult to make a conclusion about that based on image interpretation, which is subjective. Let's see, do we have a slide stuck there? Okay, that was it, yeah. Okay, let me address the question of how persistent water flowed on the Martian surface. This is an area called Nenede Valles, and it's in this area of Mars right in here, again in association with the Tharsis volcanic province. And what you see here is a meandering stream bed. In fact, you can actually see the trace of the stream bed. Now, the stream isn't there anymore, of course, but you can actually see that in the image. And one of the things that we know is that if you have water flowing on the surface, it takes a while to carve a meandering channel. Okay? It can't be done overnight. There are some places where you have alluvial fill where it can be done in maybe tens of thousands of years in some places, but more typically it takes a lot longer than that. And so the presence of a meandering channel here has provided some evidence that water, at least in some places, was not just a very rapid event that came and then went. Okay, I think the next slide, we might be looking in this area right here. And yes, we are. This is part of the Valles Marineris, and over on the right-hand side, what you see here is evidence for layering on the Martian surface, and this is a paper that was published just a couple of weeks ago in Science. What you can see here is evidence for extensive layering within an area of Mars called Candor Chasma, and this layering has been invoked to be evidence for standing bodies of water in early Martian history. Okay. Now, what we know here is that we see layering, and we see it on lots of parts of the planet. Okay, layering like this occurs in many areas. Okay, but whether or not this represents sediments settling through water, or whether it represents ash falls from volcanoes, which we also know that Mars had a lot of early in its history, or whether it represents lots of impacts with the stuff thrown out from the impact piling up on top of each other, that we don't know. Okay? And so what we need to do is study places like this in more detail. One would think if you had water, sediment settling through water, this would be a good place to look for calcium carbonate. Certainly, these areas need to be studied in greater detail. Okay, well, if there was water flowing on the surface of Mars, here's some evidence that there was a lot. Okay, here is the Valles Marineris again, and this is a Viking image mosaic, and we have color-coded topography, and we're just showing the low topography here so we can stretch out the color scale and see big variations. Okay, now over in here, this is the Crissy region of Mars, and this is the Viking Lander 1 site and the Pathfinder site, and this is actually a topographic image here, and what you can see is that there is evidence for past flow of water here, and in fact, what looks like the considerable presence of water. But this area was filled in part by water that would have come through the Valles Marineris and came up this way right here. Now, what you can see here is that on the eastern part of this canyon, though, the elevation is at least a kilometer beneath the area that the water is flowing into. So for water to have been delivered to this area right here, there must have been at least a kilometer of water in this canyon. Okay? So there must, if there was water, there was a lot of water there. And so this is evidence that there was lots of water. Okay, same area. More evidence for perhaps considerable amounts of water. Here again is the Valles Marineris, and this is the Crissy region. And what you can see on the right-hand side here, on the top is gravity data. And gravity is due to the attraction of masses, and you get gravitational attraction due to structures on the surface and structures due to the subsurface. So if you want to find out what's going on beneath the surface on Mars, what you do is you subtract away the attraction of gravity due to surface topography, and that's what's done down here, and you look at what's left. Okay, if you just had gravity due to surface topography, you would get something that looks like this here. Instead, what you see are these linear features that actually look like they're coming out of the canyons. Okay, and these are gravity lows, so they represent stuff that is less dense than their surroundings. And because they don't correlate with the topography, it means they're under the ground. Okay, so these are low-density features that are under the ground. And it just so happens that they line up, they come out of these areas where we think water flowed into the northern plains of Mars. So you can trace it all the way up here and out into here. And these things turn out to be 1,000 kilometers long and 200 kilometers wide. And in fact, what we think these are possibly buried channels. Okay? If you've ever seen pictures of the Sahara where they looked at radar images that showed streams beneath the desert, this is analogous to that, except these are huge. Okay, the next slide I think is going to show this crater right here. The evidence for layering on Mars was not confined to the northern plains. This is the Holden crater right here, and over on the right-hand side, you see this image right here, and more evidence for sedimentary layering or impact layering or volcanic layering of the surface, but just more evidence that there is extensive layering going on the Martian surface. Okay, so now I'd like to talk about volcanoes, and I would like to address the question of, well, what volcanism might have to do with the development of life, and also how volcanism could have affected the early climate of Mars and what it might have had to do with the history of water. Okay, over on the right-hand side here, you see this big area with the volcanoes. This is called the Tharsis Rise. It's 10 kilometers high. Here is one of the volcanoes over right here. This is Olympus Mons, okay, where you could fit a slug of New England within that caldera comfortably. And what you can see here is that this area is big. It actually takes up a quarter of the surface area of Mars, and we know from studying both surface and subsurface data on Mars that this is an area that has significant volcanics associated. It formed essentially from extrusion of magma on the surface and the intrusion of magma beneath the surface, and in fact we can estimate the volume of Tharsis to be 300 million cubic kilometers of magma, or about 10,000 Mauna Loas. Okay. We can see, let's see, that this is proof that this is volcanic, or at least strong evidence. These are some pictures here from the canyon of Valles Marineris, on the walls of the canyon, and you can see here what looks like volcanic outcroppings, and these go from up near the top of the canyon all the way down to the floor, 8 kilometers deep. Okay, so you can give some thought about what putting all that magma on the surface of Mars might do. So one of the questions that we have wanted to know is, did this province form over 4 billion years of Martian history, sort of incrementally, or did this province form extremely early in Martian history? Because if it did, then it means that you dumped out a lot of heat early in Mars, and it also indicates that you dumped a lot of water and carbon dioxide onto the surface and into the atmosphere. Okay. Well, what you can see here are two, if you're sitting close to the front, you can see that there are two kinds of lines here, black lines and blue lines, and I forget which is which right now, but one corresponds to the orientations or the azimuths of valley networks that we know formed in a specific period earlier in Martian history. And the second set of arrows corresponds to what tilts on the surface would look like if we calculate them due to putting together the pole-to-pole slope and taking Mars and putting the Tharsis load on it all at once. Okay, so we add those two together and we look at how the surface tilts, and if you are sitting close enough up to the front, you can see that those vectors agree. And so what that indicates is that the pole-to-pole slope and Tharsis were in place by the time that most of these valley networks formed, and we know the age of these valley networks in Martian stratigraphic sense. It's called the late Noachian, and what that means to you is that it's older than 3.5 billion years. So we know that this huge volcanic province was in place by 3.5 billion years ago. Well, if magma on Earth has similar compositions and similar volatiles as magma on Mars, if you took a Hawaiian magma and you said this Martian one has the same amount of CO2 and water, the amount of carbon dioxide that you would put into the atmosphere would give you a 1.5 bar CO2 atmosphere, which is 1.5 times the density of the pressure of the Earth's atmosphere, and it would give you a 60-meter layer of water on Mars everywhere on the surface. Okay? So here is a mechanism for giving Mars a thick atmosphere, okay, one that could be warm enough to have a greenhouse effect and warm the planet up, okay, one in which it is dense enough to rain, okay. We don't think the main mechanism of water transport on Mars was rain. We think it's flow on the surface. But it would be, you would have a dense enough atmosphere to rain, and you certainly would put enough water on the surface to do it. So this is the kind of thing that we are learning now. And by the way, this result was presented at this meeting. So this is, the pace of discovery is rapid, and this is all new material here. Okay, I want to spend now a little bit of time talking about water on present-day Mars. Okay, this is the North Polar Cap. It's a Viking orbiter mosaic, and you can see here these areas that are white. The polar cap has a layer of carbon dioxide at the top that comes and goes with the seasons as the seasons change, and one Mars year is about 2 Earth years. But most of the polar cap is made of water. And here is an image of the polar cap that you can see right here. And what we're showing you on this side right here is a photograph that shows you the edge of the polar cap. So it's essentially like taking a road cut in the polar cap. And look at the layering there. Okay, well, what happens on Mars, in the winter, it gets cold and you freeze carbon dioxide and water out of the atmosphere, and so you get a layer of white. And then in the summer, the atmosphere gets warm, and that kicks up dust, and it's very dusty, and so then you lay down dust. And so you get this, you know, ice dust, and you get a whole stratigraphic column of ice and dust. If you could go back there and take a core through that, the way we take cores in Greenland, in Antarctica, you could study the history of climate on Mars, and you could get an idea of what the surface temperatures were as a function of time on the planet. Okay, there's evidence that the polar cap on Mars was once larger than it was today. This is the North Polar Cap draped over a geologic map. And look at all of these white areas outside here. We used to think when we had Viking images, we thought these were frost, but some of them are 1 kilometer high. And in fact, what we believe, this is also symmetric around the cap, and what this actually represents evidence for is that the North Polar Cap was once a lot bigger than it is today. And so what you're seeing here is evidence for climatic fluctuations on the planet. Now, why would you have such fluctuations? Why didn't Mars just start out hot and then cool off and then nothing happens? And the reason is that the tilt of its spin axis changes, okay? This plot here of obliquity means the tilt of the spin axis. And what you can see is that right now, Mars's spin axis is tilted at about the same amount of Earth's, and of course this tilting causes the seasons on Earth. But over the course of 10 million years or so, it can go up to greater than 40 degrees. And when you get to a point like that, the poles actually get more sun than the equator does. And so the models tell us the polar caps would go away and form themselves someplace else. And so here you have more reason to believe that there has been climate change on Mars. Now we're looking at the South Polar Cap, and here we're plotting elevation. This is not a picture, and the colors here correspond to height. Well, what you can just see here on the corner of this figure here, and this goes down to about 55 degrees north, is this purple area is the Hellas Basin, okay? And if you look at a three-dimensional perspective view of Hellas, what you find is that the southwest rim of the basin has been scraped clean, okay? If you look at the basin, you can see the roughness around here, and this has been scraped clean. And there are a number of ideas for how this might have happened, but one that has probably gotten the most attention is that it's a straight shot here from the South Polar Cap to Hellas, and that you once had a much larger polar cap, and essentially glaciers flowing north, because we know everything flows north. And so the Hellas rim may have been modified once in the past by glaciers. Okay, well, one interesting question that we can ask is that now we have quite good measurements of the surface of Mars, and how much water is there, and how does this compare to how much water there was? All right, well, in terms of what we see on the surface, how much water the planet has at the present is the water that's contained in the North Polar Cap and the South Polar Cap. And if you add that together, you find out that the best estimate is about 20 meters global equivalent layer. That means you take 20 meters of water spread everywhere on the planet. That's how much we see on Mars today. Okay. Now, if you go down here, you see lots of estimates with big errors for how much water Mars might have had in the past. Okay. And the numbers bounce around all over the place, but for the most part, they are much greater than the water Mars has today. Okay, so the question is, where did all this water go? If Mars had all this water, a kilometer of water in Valles Marineris and enough to make 1,000-kilometer long channels in the northern plains, where did this water go? And there are models for how much water you can lose out of the atmosphere, especially once Mars's magnetic field shut off. The solar wind could come in and dissociate, break apart molecules in the atmosphere, but you find out you can't lose close to the amount of water that you need to lose to explain the discrepancy of what you have and what you think you had. And so that leaves us with the conclusion that most of the water that Mars used to have, it still actually has. Okay, and here's some evidence for this. On the left-hand side here is a crater that is called a Rampart Crater. And this stuff around here is stuff that was thrown out of the crater when it formed by a meteor impact. It's called ejecta, and this is called a rampart. It essentially looks in a planet that doesn't have an atmosphere and that doesn't have water in the subsurface. You just get a nice rays coming out of it. But when you impact into a water-rich substrate, you get something that looks like you threw a rock into a mud puddle. Okay, and over on the right-hand side here is a topographic image of the northern hemisphere of Mars down to 55 degrees latitude. Now, if you just looked at a regular camera image of Mars, you wouldn't be able to see the detail here. This is showing you subtle slopes, and the people up at the front will be able to see that any crater that is not buried actually has one of these ramparts around it. Okay, so there is evidence here that most of the water that Mars had is still there, and it's in the subsurface. Okay, some evidence from this past summer has indicated that perhaps liquid water still occurs on the surface of Mars occasionally, perhaps due to these climate change cycles, due to the spin axis tilting. Okay, over on the left-hand side here, you see evidence for these features. Here's some more evidence over on the right-hand side here. Now, first of all, there are two hypotheses here about this. The first is that these are due to water, and the second is that they are due to water that recently flowed, as opposed to water 4 billion years ago that flowed. Okay, here's some good evidence here that it's recent. Here these cut dunes. Okay, dunes are very transient features on Mars in a relative sense. So if they're cutting sand dunes move with the wind, and Mars has plenty of dust and it's plenty windy, so dunes move. Okay, and this would tell you that we don't know how fast the dunes move or how much material is actually being moved, but we're talking about millions of years here. I mean, in geology, a million years is the same as today. You can't tell the difference between today and a million years ago in geology. All we know is that it's recent. Okay, and so the question is, how do you get this? And there have been no satisfactory answers for this yet. In fact, we know that they are recent. We are not positive that they're water. There is some suggestion that this could be just dry material coming downhill here. Most of these occur on steep slopes, but we've looked at some of these, and some do occur on slopes that are shallow enough that it doesn't seem like dry material would just be transported down. There are slopes below the angle of repose that you see some of these coming down on. And so some people have suggested it's not water, it's liquid CO2. That requires much higher surface pressures, 6 bars of an atmosphere. So it turns out to be more problematic than water. We don't know the answer of what's going on here yet, but there have been a number of talks at this meeting that have begun to investigate how this could be explained. Well, I know you people in California don't get to see snow much, and so here is some snow. This is the North Polar Cap of Mars, a three-dimensional view. The volume of this is about half of Greenland in terms of the ice content. Over on the right-hand side here, this is a view. This is actually going across the South Polar Cap. But what you can see here these are laser returns from the Martian atmosphere. And we know from doing the thermodynamics that this corresponds to CO2 condensing out of the atmosphere, and this is during winter in the southern hemisphere. And so what you are looking at there is dry ice snow. And in fact, we can even measure how deep the snow is on Mars over the course of the winter and how much it snows. Okay, so where do we go from here? Okay, we clearly need to continue to study Mars from orbit in a global sense, but we also need to get down to the surface to start looking at the chemistry of the surface, because many of the questions that remain unresolved deal with trying to understand chemistry. But we can't make all of the geochemical and geophysical measurements that we need to make of Mars in place on the surface. One of the things that we really want to know is how old some of these rocks are. That cannot be done on the surface of Mars in a rover like this, and this is a schematic of the rover that's going in 2003. There are some things, like getting ages of rocks, that we have to bring samples back to Earth. And so bringing back samples from Mars is a high priority for those of us who study the planet. We thought it would be interesting to have a picture of Earth from Mars, but this just goes to show you how difficult it is to do science sometime. This is a picture that was taken from Pathfinder, and in order to take a picture anywhere, it takes a huge amount of calculation. Where should the camera go? What do the settings have to be, et cetera, et cetera, et cetera. So it turned out there was going to be a time when Earth was going to be in the picture, and they decided to try to take a picture of Earth from the surface of Mars, which would, I think, be rather a compelling picture. But what happened is they turned the camera skyward at the appropriate time after doing the appropriate calculations and got the first picture of an overcast sky from the surface of Mars. Okay. But we are going to be going to Mars. We are going to be sending rovers. We will be sending people at some point. Right here is one of the areas that is a candidate landing site for the 2003 rover that I just showed you. This occurs at close to latitude 00, okay, on Mars. And what this red here corresponds to are some observations taken by a thermal emission instrument orbiting Mars right now. And the red corresponds to coarse-grained hematite, and hematite is Fe2O3, and it is a mineral that forms due to precipitation of mineral in standing water. And we know from the spectral signature that the grains are large, so it was water that was sitting on the surface for some period of time. And over on the right-hand side here shows you the geological context of this region. And you can see here it looks like there is a big deposit that has flowed on the surface. Okay, and this is one of the places that the 2003 lander might go. They're looking at a number of places. This one, certainly there is evidence for past standing water, and if it can be viewed that this is a safe enough place to land, this is where it might go, not to presume what the process that NASA will take in the selection will show. But what I've decided to do to end the talk here is to show you a video where we're going to come in and fly over some interesting places on Mars. And we're going to end by landing right here at 00. And so in the, what's it? Okay. Okay, and so again, what you're going to see is color-coded topography so that you can see detail, but we're going to start this out here, I think, looking at the Hellas Basin. when this comes up. And okay, there's Hellas, and then we're going to come in over the South Pole and look at the southern layered deposits there. One of the interesting things is that you see these spirals in the North Pole, and these are features that don't occur on the Earth. They are unique to Mars, and here we are, we're coming up north now, and we are going to cross over the very western part of Valles Marineris, and now we're going into the Tharsis province. And this is the volcano that I showed you a picture of, and now we're coming up over the Tharsis province, and we are going to be, now we're in the flat northern plains of the northern hemisphere where people think there might have been an ocean, and now over the North Polar region. It's thought that these spirals could be due to winds blowing off the pole as the planet rotates, but they go in the wrong direction. And so the only way to explain them is to spin Mars backwards, by the way. And now we're coming to the south, and we will be coming up past the Olympus Mons volcano. They're the largest volcano in the solar system. And we are going to fly through Valles Marineris right here, which is the floor of Valles Marineris is, by the way, quite another interesting site where we believe there was water, and that's another candidate landing site for 2003. Now we're going through all these chaotic regions where it looks like catastrophic, huge amounts of water once flowed, and 0 marks the spot. And of course, it would never really happen this way because celestial mechanics and fuel argue against doing this kind of landing sequence. We'll go through it one more time here. These features here are also have glacial analogs and could potentially be due to the melting of polar material earlier in Martian history. These are some of the oldest terrains on Mars right here that we are flying over. And you can see some of the ramparts there on the craters that we're passing over. That's an ice-filled crater right there. Okay, then down once more through Olympus Mons, and coming in over some of the smaller volcanoes and faults in this region, and once again through the canyon system. And I'll just close here by saying that would that it were as easy as it looks. And that's it.